So now Newton recognizes that the force of gravity is proportional to 1 over r squared. But he also knows that an object experiencing a force of gravity due to the Earth has a force proportional to the mass of that object. The force is mg. So he deduces from that any time I have a force of gravity from object 1 on object 2, that force is going to have to be proportional to the object experiencing the force. That's what we had here, the object experiencing the force, m2. But we also know that tells us that the force from 2 on 1 would have to be proportional to mass 1. But by action-reaction, these two forces are equal to each other, which means the force from 1 on 2, which equals the force from 2 on 1, had better be proportional to both m1 and m2. And we already found that it was inversely proportional to the distance between them squared. So here we have that. We have two objects attracting each other gravitationally. We know that the force of B on A equals the force of A on B. They are both gravitational forces. They are always equal and opposite. And the force is proportional to the mass of A times the mass of B divided by the distance between them squared. And this is true of any two objects in the universe, which means you have a gravitational attraction to everyone near you. In modern terms, we say that the force is equal to the universal gravitational constant, capital G, times ma times mb over the distance between them squared, where the universal gravitational constant is 6.67 times 10 to the negative 11 newtons meters squared per kilogram squared. So now we have a slight problem. We've learned that the force of gravity decreases as we get further from an object, but we know that the force of gravity is essentially constant here at the surface of the Earth. Well, the resolution is, first off, to recognize that the distance in the equation, F equals G m1 m2 over r squared, is the distance to the center of the Earth. And most distances that we deal with on a daily basis are very small compared to the distance from the center of the Earth to the surface of the Earth. So because of that, if we consider ourselves right at the surface of the Earth's mean radius, we get an acceleration due to gravity of 9.8 meters per second squared. If we go 8.8 kilometers up to the top of Mount Everest, as high as any point on the surface of the Earth is, it decreases to 9.8 meters per second squared. Really, to two significant figures, there is no decrease. Okay? Recognize this is only 2 parts per 100. So in other words, any additional change would be in further digits down here. And there is a little bit of change in the 3rd, 4th, and 5th significant digit. If we go to the highest distance that manned balloons ever get to, about 36.6 kilometers, then gravity drops all the way down to 9.7 meters per second squared. Even if we go all the way to the height of the space shuttle, where the space shuttle orbits, gravity only drops to 8.7 meters per second squared. And at that point, we are 400 kilometers above the surface of the Earth. Note, that means that the force of gravity is not zero at the space shuttle's orbit, which means weightlessness is not caused by having no gravity. If we go up to the highest satellites we send, or some of the highest satellites we send, the geosynchronous communication satellites, that's almost 6 times the radius of the Earth, so we would expect it to be 1/36th the acceleration, and that is about right. It gets down to about 0.2 meters per second squared at the geosynchronous satellites. So you see, we have to get very far from the Earth before gravity starts dropping significantly.